Okay. So we're starting with Wilhelm Schlag, and he's going to talk about his work with Jonas Riemann on the stability of the soliton for the Klein-Gordon equation.
Thank you very much. It's great being back here for actually not so little working group, right? A large working group. I might have to disappoint you, Benoit. I'm not sure I should be giving a research talk. Yeah. No. So you kind of announced it like a research talk on my work with Jonas.
I don't know, it's just for the purpose of because it's recorded.
I see.
At the beginning, we know what the material is for. So
can I write here?
To official.
Can I write here?
Yes.
All right. So let's remember what the ultimate goal is, at least as of now, is to study the problem that Benoit presented when we first met in October. And with a repulsive Coulomb potential. Now, this is in R3, which is very important. And I think it's fair to say that this is a hard problem. What Patrick Flynn spoke about is if you omit this term, then Katakusateri 10 years or more ago showed small data scattering for this. Now, why is this a hard problem? Let me just remind you, because it will set the stage for the one-dimensional problems I'll talk about in a moment. Why is this a hard problem? Because if you look at the Schrödinger decay, this is all extremely standard. In 3 dimensions, you get this, all right? This, of course, comes from the form of the fundamental solution of the kernel of this fundamental solution is constant t to the 3/2. All right, so the kernel will be absolute x minus y, and you immediately get this pointwise viscosity k. And we're interested in this Cauchy problem, again, without this for now, for small data. So then we have colored shock. I always like here. So then this looks very good because it will decay. If we think of writing the Duhamel formula for this, let's cross it out. The Duhamel formula, then we expect the square of this. So this decays like t minus 3. Okay, so that's perfect because if we write down the Duhamel formula and do energy estimates, then this is integrable from 1 to infinity. So it converges, and we can treat this term perturbatively. If the solution, if the data is of size epsilon, this is also of size epsilon cubed. So everything looks perfect. What makes this less perfect is this minus Laplace minus 1, and Patrick, where are you? Forgive me for kind of repeating things that you explained, but this was in October, and maybe some were not here, or we won't remember. So minus Laplace inverse, the Newton potential has a, of course, explicit form in 3 dimensions. So if you look at the kernel of this Newton potential, it's 4 pi x minus y, right? Something like that. And now what's the effect of this? Here we have to be a little bit careful. Not only does this decay, but we would expect that the solution lives on a ball of size t. After all, right, the Schrödinger equation is some quantized version of Newtonian mechanics. So we expect, and I can explain this more by stationary phase if anyone wants to see. So we expect that after time t, the bulk of the solution will live on a ball of size t. Agreed? So then, if you look at this kernel, in effect, what you have to do is you have to integrate from 0 to t r squared dr. But that's t squared. One of r comes from the Newton potential. R squared is the polar coordinates. and you see that you get t minus 3 times t squared. Aha, so this term actually can only be expected to decay like t minus 1. Okay? And this is an explanation why this is such a hard problem. You cannot simply treat this perturbatively via Duhamel because it diverges. And many deep problems in analysis have to do with logarithmic divergences, same with Kelvin signal theory. So logarithmic divergence after all, right? Hilbert curve. All right. So the problems I will discuss, and so Benoit, maybe I will go on this board, are long range potential. Yes, long. This is called long range. And those of you who do scattering theory, linear, nonlinear, you will realize that you can't hope the standard wave operators to exist, right? You have modified wave operators. So you can't hope to approximate, even for small data, the flow of this problem to leading order by that. Does not work, cannot work. So what models will I consider? They have a conserved energy, let's call it just E. They're one-dimensional. So U, UT, maybe I'll be lazy and just write E of U. It's 1/2 UT squared. This is the Hamiltonian. That's W of U dx. From minus infinity to infinity, I'm suppressing the variables. U is a function of t and x. So this is my Hamiltonian where, well, at the minimum, your Hilbert space H should be H1 plus L2 of the line. So that this makes sense. And of course, OU what W is. So W is the potential. And throughout the talk, I will focus on 3 examples. Benoit mentioned in the title announcement, nonlinear Klein-Gordon. All right, so W of U. Let's look at 3 different examples. And actually, I should have written phi, never mind. And here we have 1/2 U squared minus 1/4 to U4. Okay, so this is called phi 4. This is the potential energy of phi to the 4 on the line. This gives you Stein-Gordon, and I'll write all these PDEs in a moment. And this is NL KG3. This is nonlinear cubic Klein-Gordon. What do the PDEs look like? Please stop me. It's a very informal gathering. So stop me whenever there's a question.
It's the focusing.
Yes, so this is focusing if I got my signs right. We'll see in a second if I did. So associated to this Hamiltonian, there is a Lagrangian. Maybe I don't have to worry about that. You're looking for the critical points. Well, maybe I am going to worry about that. And forgive me if I now switch to phi. So above I wrote U, now I'm going to write phi. This is just an ingrained habit. I have used U in the first place. Then I have minus 1/2 UT squared plus 1/2 UX squared plus WU. And the strange thing about this is that we have to integrate over space and time. It's a formal object. So here we have R1 plus 1 here.
So it's the phi in U.
Phi equals U. Great. I'm hopeless. Okay. Phi equals U. So what are we looking for? We're looking for the critical points of the Lagrangian. And if you do this calculation, you can do it in your head. What you will find is phi tt minus phi xx plus w prime phi equals 0. So you have a 1D wave type equation. And so let's just follow our list. The fundamental phi 4 problem is phi tt minus phi xx. Then you have, look carefully at these signs. They are strange because you have minus phi and then you have plus phi cubed to 0. So just take a few seconds to think about why this is a strange sign. And then you have phi tt minus phi xx plus sine phi equals 0. And finally, phi tt minus phi xx plus phi minus phi cubed equals 0. This is sine Gordon. This is focusing, if you want, NLKG3. Okay, these are our three players. 1D wave equation. Now, what are the pictures of our potentials? Maybe I'll draw them. Where should I draw them? Our potentials look like this. So phi 4. This is phi 4. Okay, sine Gordon. You know what 1 minus cosine looks like. Doesn't it look like this? But it's silly of me to even draw that. And so this is the sine Gordon. What is this? This, I suppose, is phi, and this is W of phi. This is the graph of W. And for what does it look like for that thing over there? Here we have this. No, other way around. Silly. Your positive definite, exactly the reflection of it. Your positive definite for small u. So like this, like that. This is focusing NLKG3. All right, so these are our three potential energies. Now, why did I say that this is a funny sign? Let me just briefly dwell on this. How paradoxical, right? That we just flip signs to go from here to there. Well, because if you Fourier transform, you see that you have the symbol psi squared, but then you're subtracting 1. So this is nice, positive, this elliptic. But when you subtract 1, you see that for c less than 1, you lose ellipticity. What this means is that the zero solution makes no sense. And indeed, the zero solution, plug it into the Hamiltonian, it has infinite energy. All right? So here, the zero solution makes perfect sense. Here, it makes perfect sense. Vacuum states, if you want to call them that. Here, it makes no sense. So what does make sense is that we look for time-independent solutions. We look at minus phi xx plus w prime phi equals 0. And now help me draw the phase portraits of these three models. I always have to draw these three models phase portraits. Let's start with phi 4. What do I mean by phase portrait? I mean, of course, that you look at the phi prime plane, realizing that if you multiply this by phi prime and integrate, you get an algebraic curve. Or in fact, for sine Gordon, it's not algebraic, it's transcendental, but never mind. You get 1/2 phi x squared plus w phi equals constant. Right? And so you look at the level sets of this, and what does it look like for phi 4? Notice that constant 1, constant minus 1, look at the graphs. I didn't label the act, I mean, I didn't put numbers at the minima of W, but they are minus 1, 1. And so what you find is that you have a heteroclinic orbit, then this is elliptic, this is hyperbolic, so that if you look at the Hessian here, it has positive, negative eigenvalue. This is the phase portrait. Let me quickly do the sine Gordon phase portrait. Well, that's the physical pendulum, but we normalize in such a way that the so the upper angle, concentrate for a moment. So I think this is our phase portrait, correct me if I'm wrong, where this is of course 0, this is 2 pi, etc. It's 2 pi periodic around pi, you elliptic, and then like this. Okay, you with me? And this, of course, is a bad picture. And now here, totally different. Here the phase portrait looks like that, and here you again have minus 1, 1, then it's like this. Now notice these very special orbits, I call them heteroclinic orbits. This is the special guy, this is the special solution, and the should be perfectly symmetric, can't draw it like that. Here you have another heteroclinic orbit connecting equilibrium, and it's 2-pi periodic. And here you have a symmetric pair of heteroclinic orbits. Homoclinic, connecting zero vectors. All right? Just to state the obvious, what is this red orbit for the pendulum? Here is a pendulum, and you measure the angle from the unstable top position. Then there is one trajectory which in infinite negative time approaches this, swings around, and in infinite positive time approaches this. It's unique, and it's these family of red orbits. Just to state the obvious. Now notice, this is separable. You can explicitly integrate, right? Never mind, you see, you take the root, then you do d phi dx, you separate, integrate. Not surprisingly, this so-called Kinks solution, this heteroclinic orbit, which you don't see from this Higgs portrait, has an explicit form, and it is tanh for phi 4 x root 2. Here, this one is k of x, k for k 4 times arctan e to the x. And here, this is no kink, it goes from 0 to 0. It's q of x is root 2 step x decays nicely exponentially at both ends. You can immediately read off from the equation that it has to decay exponentially at ends. So explicit solutions, they're not unique because you can translate x by anything you want. So you have translation invariant. The PDEs are Lorentz invariant. So you generate an infinite family, in fact, a manifold of moving special solutions. Why are they called kink? Well, because look, graph the tanh, right? Graph this. Now here, this Q, this is not called kink, it's a soliton that's very nicely localized, and there are two of them, plus minus, unique up to a translation, x minus x naught. Okay? So guess what you do next? You want to go ahead.
No, since we're questions, we're left in the class. We say that the relevance of this is that this in physics would be the states that cannot decay to zero because it's topologically what they call
correct. That's why maybe in my title or abstract, I don't know, did I give you one? This is called the topological soliton because it has non-trivial charge. What is the charge? The charge is also written Q, has nothing to do with this Q. And for the field, it is phi x of tx dx, which of course, so this equals the charge. I don't want to write Q, even though in physics books I think it's called Q. You will say, well, that's silly because that's just phi of t infinity minus phi of t minus infinity precisely. What's the point of doing this? You differentiate this charge, you get phi xt, and then you see that that is zero. So this charge is conserved, and you cannot jump from one topological segment to the next because that takes infinite energy. Everything has to be finite energy. Agreed? This was your comment.
Because there's very few Nobel Prizes winners, but Kosterlitz who won the Nobel Prize for physics, topological protected states.
So you set the bar for this working group very high. Nothing short of a Nobel Prize or Fields Medal for this group. Eh? Well, the young ones, yeah. I'm too old for work. I cannot speak for our other senior. They're young enough to do it, I'm too old. So the next question is, of course, stability of these creatures. So what happens if you perturb around them? Right, so how did we start? We started with the nonlinear Hart tree, and we said small data. That means you perturb zero, the vacuum state. Here we have precisely other questions. We're perturbing around a big guy, the soliton, or we're perturbing around something with non-trivial topology, right? It's around the king. So be it as it may, we now write phi is k plus u. This is why I wanted to use phi and not u. This is small. And then, of course, you linearize. So you stick it into these wave equations. Luckily, they're all written here. And guess what you will find? You will find UTT plus HU equals a nonlinearity. But this nonlinearity, we want to expand H, I will tell you in a moment. It's just a Schrödinger operator with a potential and shifted by a mass term. We'll tell you in a second, but the nonlinearity will be, we want to expand it because U will be small. And we can write it in this form, possibly with higher order terms. And you see, if I go to U4, things should not be so badly behaved as long as this a linear part has enough dispersion, enough L infinity decay. So what H's do we have? You see, I have to drag along all of these three examples. I might stop at some point, but I owe you what these H's look like. So for phi 4, you have to remember it's minus cx squared plus 2 minus 3 sketch squared x over root 2. You see, so you have Schrödinger, then you shift the continuous spectrum by 2, and this is a beautifully localized Schwartz function. Then, so this is what you get for, if you linearize about phi 4, then you linearize St. Gordon, then you linearize about focusing NN33. So for St. Gordon, you get minus dx squared, I think plus 1 minus 2 sec squared x, and here you have minus dx squared plus 1 minus 6 sec squared x, why 6? Because 6 is 3 times 2. The 2 you get by squaring this guy, so you have 2 sec squared times 3. It's this. Okay? Make sense? And where does the 1 come from? Well, the 1 comes from this one. This is a linear term, and it has a good sign. Okay? Now you might say, but please do these calculations. You will say, why do you get something localized if you linearize about a kink? Well, it's important actually here that this kink takes the same value in absolute value at here and here, minus 1, 1, because you have to square this creature, and then you approach 1, and that 1 is part of this 2, okay? The rest is localized. So here are the equations, and then of course you want to know immediately what are the spectra of these operators. Whenever you want to linearize, the first thing you have to look at. Why? Because, well, everybody knows if this guy has a negative eigenvalue, you're exponentially unstable. You have non-trivial index. Yeah? This can go. And so what are the spectra? They look like this. In the same order, 5, 4, St. Gordon, NL, occasion 3. 0 in all cases is going to be an eigenvalue. Why? That's very clear because you have H of K prime is 0. What is that? That's the translational freedom. So when you differentiate in an infinitesimal translation, you get that the derivative of your soliton kink is a 0 energy eigenfunction. Agreed? It's an eigenfunction with eigenvalue 0. Now, so 0 has to be an eigenvalue in all cases.
If you repeat why we know that.
Yeah, yeah, of course.
That's it.
Of course. Where is my nonlinear here? These are all translation variant, right? So if you now take phi equals k, but do x minus y plus 1, y is fixed, then first of all, this goes away, then you have this equals 0. Now then take a y derivative and set y equals 0. then you get, of course, a solution of the linearized problem. Make sense? And that's what this is. So this is the infinitesimal translation. Infinitesimal translation invariant. Now, for phi 4, we start at 2. As you can see, where are they? Up there. And then here is something very, very important and mysterious, is that you have an eigenvalue in the continuous, no, in the gap. The continuous spectrum starts here, goes all the way to infinity. So you have a zero energy, different color, zero energy eigenvalue. You have the 3/2 continuous spectrum. For phi 4, you have the translation mode. Then you go from 1 to infinity. Here you have the translation mode. But look at this. Can you tell me why you can immediately read off? What is the eigenfunction associated with the zero mode? It has to be the derivative of such. Don't try and compute the derivative of such. Who cares what it is? But you are positive, you're negative. Slope positive, slope negative. So it means you cross 0. You have a 0. So the eigenmode with eigenvalue 0 has a crossing, has a 0. So therefore it can't be the ground state. In fact, it has to be the second state because this guy has a unique 0. Are you with me? So by Sturm oscillation theory, you must have a negative eigenvalue, which I think is negative 3/4. Don't quote me on it, not important. So this is the ground state. So the eigenfunction associated with the ground state is always strictly positive. And then again, we have our continuous spectrum starting at 1. Okay? This is what the spectra look like. You can immediately read off from this. Look how cheap this was, but completely rigorous. Just look, differentiate the Q, you have a crossing, can be the ground state, therefore negative spectrum. Therefore, the soliton Q is unstable for LKG3. Cheap. Are you with me? Because how does this work? Suppose H, and I'll name it here, NLKG3 of some function G is minus 3/4 G. What does G look like? It has to be positive and exponentially decaying by what Ibra spoke about. Agmon metric. Negative eigenvalues have to decay exponentially. This guy too, because both of them are negative eigenvalues with respect to the threshold. Ibra just needed to be to the left of this point. Then every mode here decays exponentially by this Agmon metric. So if there is such a G, then stick that G into the linearized problem, which is what? It is look for a solution which is of the form U of T and X is some function coefficient A of T G of X. D looks like this. And now what ODE does this have to satisfy? Particularly for these trivialities, A double prime. Where are the linearized equations? Up there, UTT plus H. So you get A double prime. What is plus H? So you get minus 3/4 A is 0. Agreed? What are the solutions? What a trivial question. E to the plus minus root 3/4 T. Yeah, well, the plus 3/4 T sends you to infinity. It's exponentially unstable. Okay? So in the language of dynamical systems, you would rewrite the linear part as a system, so a Hamiltonian system, which you can always do for U and UT. And then you have a matrix operator, you have U and UT. And here you get 0, 1. And don't you get minus H0 there? And now you recognize that this is symplectic matrix times H0, 0, 1. The symplectic matrix had better be minus 1, 0, 0, 1. Right? So this matrix operator will then have a pair of eigenvalues. And the pair of eigenvalues have to be this root 3/4 minus root 3/4. And those of you familiar with invariant manifolds, yeah, well, this will give you the one-dimensional unstable manifold. This gives you the one-dimensional stable manifold with regards to forward time. Okay, so. And where does the center stable manifold sit? It comes from the bulk of the spectrum, which sits on the imaginary axis. Are you with me? Because the linearized evolution will be e to the t j. Give this guy a name, A, J, A. Okay? And the spectrum of JA will lie here, subset there, and these 2 points. Okay? So, now, I'm doing horribly on time, but is there a time limit? 2 hours, 3 hours? No. No, I want to achieve like that.
We have a train.
We have So now, it won't surprise you to see the following theorem, which is ancient. It's from the 80s, and it's Henry Paris Brzezinski. And what it says is that the kinks, not the soliton Q, because we know that's exponentially unstable. You need a center stable manifold to stabilize it. But here there is no negative spectrum. So what do they say? They say orbital stability of K or 5,4 SG. Sine Gordon, look at that paper, it's more general, not just these, but I just presented those 2. And it says that given epsilon positive, there exists delta positive such that if you start with data, let's use the first 2 lines up there. Phi minus K by T at time equals 0. This is time equals 0. And in the energy, this is less than delta. Then phi minus K, leave some space, at all times in H1 cross L2 is less than epsilon. Do you believe this? Since I'm asking such a stupid question, I must have set you a trap. What is the trap? The trap is that if you perturb the kink, it will start moving because you have the translational mode. Well, if it starts moving, then what you have to do is move it. So you have to take the infimum over all possible translation. So you have a one-dimensional family of kinks, and the statement is orbital stability. That of course doesn't mean that if you start close to the kink, and I could put any translation I want here, cannot be that if I start close to the kink, I remain close to the kink. No, you stay close to the kink family because of the translational freedom. How do I kill this translational freedom? For example, if I say that phi t are odd, you see, if they're odd, then you remain odd. Just look at the symmetry of the PDE. Yeah, then this y has to be 0. The infimum has to be 0, has to be a viable choice. And there is a very sophisticated challenge you could give me, because when you perturb the kink arbitrarily, there is more than translation symmetry. What other symmetries do we have in the problem? Lorentz symmetry. Why do we not see Lorentz transforms here? Why don't I have to Lorentz transform K? But if you want to Lorentz transform K, there's nothing to be afraid of. In fact, very important to do so. So phi tx equals K relativistic factor x minus PV is another solution where gamma is 1 minus v squared minus a half. Of course, you cannot be faster than the speed of light. That is a solution. Okay? And if you perturb the kink, you will excite all symmetries. You will excite translation freedom, but you will also excite this. Tell me why I don't have to worry about that. Because the v will be very small depending on delta. Okay, and when it's very small, this will be close in H from cos L2 to K itself. You can absorb this into that. You see it? Gamma will be very close to 1, and then you can absorb it here. That is why you do not have to worry about the length transforms. Otherwise, this would be a total lie. How do you prove this? Very easy, quote unquote. You use the energy as a Lyapunov function. Why? Because here, not here, but here the spectrum is positive, meaning what? That you have coercivity of the associated quadratic form. And the coercivity is, let me write it here, H, which variable u is greater to constant non-u H1 squared if u is perpendicular to the zero mode, which is K prime. Okay, that's the coercivity. And this coercivity then tells you that by conservation of energy, this will control these distances for all times. And where do you get the orthogonality condition from? From here. Your optimal choice of y will guarantee you this. Very logical, isn't it? Because the obstruction comes from the translational freedom. So you remove the obstruction by means of the translational freedom. It's very logical. So then the next hurdle that was on the horizon and always considered much, much harder is asymptotic stability. So in other words, can you say that this tends to 0 and time tends to infinity, not just less than epsilon? So could it be true that if you make delta small enough, that then this tends to 0 as time tends to infinity? Impossible, because the energy is conserved. So how could all the energy converge into here? Where does the rest energy go? Because the energy will decouple. It decouples between this bulk term and the so-called free field, whatever that is. They become asymptotically orthogonal. So the energy will split into the energy of this plus whatever excess energy you had here to begin with. Does this make sense?
I guess in this case, not just that, but it would split into a Lorentz boost, but the small Lorentz boost.
The smaller Lorentz boost would also kill the asymptotic stability, absolutely. So it's just hopeless, okay? Now, let me write in color. I can do this, it's cheating, but another theorem, much later, around 2015, by Mattel, wrong alphabetical order, Kowalczyk, Mattel Munoz. They have not orbital, they have local asymptotic stability. Can you read this? Local asymptotic stability. Very important, they have to assume phi odd. Hopeless, you can't use their method if this starts moving. Then you cross out this. Terrible board work, I'm lazy, trying to save time. You don't have to translate. What does local mean? It means that you have to put here, then you have to eliminate this. There exists a small number such that if you're close in energy, then this tends to 0 as time tends to infinity, locally for any compact in. This is the hard result. How do they prove it? Well, that's a good question. There is a somewhat, they even rely on some numerical piece where they have nothing wrong, nothing against that, some spectral properties. They eliminated this only last year, I think. There is a paper by Kowalczyk Mattel from 2021, 2022, please don't quote me on this, where they redo this in a very, very clean and amazing fashion. The way they do this is by some cleverly constructed virial arguments. But notice something, there are several amazing things about the Kowalczyk-Mattel-Munoz theorem. What about this internal mode? Why is this confusing? Because look what we did here. This was for NOKG3. Now let's change this. Let's do it for 5-4 with the internal mode. So we get plus, it doesn't matter what the number is, but we have plus 3/2. Should have written it in red to match this. You look for this, then you get that. What is this? A double prime plus 3/2 A equals 0. What is that? The harmonic oscillator. Okay, so you get a harmonic oscillator. Instead of exponential instability, you just sine cosine. Yeah, that's a disaster because if you have sine cosine, then you don't go to 0. The locality doesn't help you in the least because the mode is exponentially decreasing, so it is local. Not compactly supported, but tiny tails. Okay? So what on earth is going on? Well, you have to use a very delicate phenomenon that I don't want to get into, which is to couple this discrete mode to the continuous spectrum by means of a Fermi-Golden rule. That's a whole topic unto itself. And it is a purely nonlinear effect. So by a purely nonlinear effect, can you remove this non-decaying mode and force decay? So if you want to see this done for the first time, there is a pioneering paper, FRG, Fermi-Golden rule, in 3 dimensions for some concocted nonlinear Klein-Gordon equation with a potential. Who did this first? Remarkable paper by Sofer, Weinstein, in Invenciones around, I don't know, 96, 97. Okay? Please look at this remarkable paper. You will see there that via a cubic nonlinearity, they coupled this to that. How do you couple? We have a quadratic nonlinearity. There is a silly little inequality that makes the coupling possible, and it is this. Because the coupling to the continuous spectrum is quadratic, the frequency, which is √3/2, if you double it, which the quadratic term will do for you, you have to end up in the continuous spectrum. Okay? And then there is a non-vanishing, a resonance condition. Very important. Resonance means what? Small divisor. Okay, there is a small divisor that then is responsible for the nonlinear decay of this. Delicate. In the end, this will satisfy a quadratic Riccati equation. And this Riccati equation has the good sign. That's why the Fermi-Golden rule is a non-vanishing of a quadratic form involving the resolvent in the continuous spectrum precisely at this number, 2 times √3/2 in our. Okay, makes sense? You need a sign. Imaginary part of some expression has to be positive. That's Fermi-Golden rule. Now, can this theorem be true for sine Gordon? No. Okay, this is a delicate thing. For sine Gordon, there is something called the sine Gordon. I haven't mentioned this at all so far, which is a terrible omission. Sine Gordon is special because it's completely integrable. It allows totally different method. It has lax pairs. It has you can approach it by a Riemann-Hilbert d-bar. You can use spectrum transforms. There is the magic of the completely integrable PDEs. This magic is absent for 5-4 and nonlinear Klein-Gordon. Okay. Now, for sine Gordon, this cannot be true because there is a creature. Completely integrable equations have many mysterious properties, including mysterious solutions. There is something called a wobbling kink. What is a wobbling kink? I think it's self-explanatory. You take your kink, and then there is a time periodic version of it where it goes like this. Bad picture, but you understand. Wobbling kink. Look it up on YouTube. Okay, you'll see what they look like. If you have a wobbling kink, you can never do this, right? Because locally, you will, this defect will not go to 0. It will oscillate. Okay. So what the Kowalczyk-Matej-Milnow's theorem proves for the first time is that this non-integral 5-4 model doesn't have a wobbling kink. Wasn't known before. Okay.
So this could work, assuming that the wobbling kink is far from the kink.
It's very close.
To
These
close an
pictures are
app,
very close.
press Command Q on your keyboard.
You can
If that doesn't
add-
work,
so
open the Apple menu and choose Force Quit.
You can find the wobbly key. That's true.
To any epsilon delta, you will find a wobbling energy close to it. Then Sine-Gordon has another family of creatures, has breather solution, which are localized, exponentially localized time periodic solutions. Those are not a contradiction to anything because they're hugely far away from the Kinkian energy. Okay? So now, finally, I get to things which are considered kind of modern, but this is also modern, but it goes in a very different direction. It stays within Lyapunov stereotype methods. Yes.
Maybe before we go to the model, because there is one thing that I find amazing about the Sine-Gordon equation is that it was written down by Chebyshev on his work on how you could put some code on the sphere.
I thought this was done in Paris in the 1860s, no? Didn't the famous French geometer Monge write this? The Sine-Gordon equation comes up as Gauss-Codazzi of the pseudosphere. Gauss-Codazzi of this.
Okay, so if you want to put some close, so you don't need to have an orthonormal frame, you just need to have a frame of vectors that are always of unique length.
Mm-hmm.
And then you can bring on the sphere.
Mm-hmm.
Well, remove the scene.
Okay, and what do you put on the? I didn't understand fully what Chebyshev put on this.
So Chebyshev, I think, was in charge of the uniform for this.
Oh wow! So he was dressing the military and needed the Sine-Gordon.
And that's the sphere. And prove that you cannot remove the scene in time, and you need to solve the Sine-Gordon equation.
So you see, the distinction between pure and applied mathematics is artificial, which is one of the little things I believe in.
Apparently, you can math and fashion.
Yeah, math and clothing. So now where I have more experience with over the past 2-3 years is when you don't work in energy, but you work in infinity and you don't localize. Okay? So let me try and write down some theorems. So we have a theorem. This is Luhrmann, who is at Texas A&M, and this happened in 21. It says that the kink for Sine-Gordon is asymptotically stable in L infinity, but only for odd perturbations. At the moment, we're working on dropping the oddness, and the kink moves. Okay, so there exists epsilon positive such that if, again, we need to separate our initial data. Let's just call them phi0 minus the kink and phi1, and then we need enough weights, which is important that we only use one X weight. And then I think it's H3 cross H2. We need more than energy. This is small. Okay, so we need a weighted Sobolev space. And all of this has to be odd. I can't emphasize this enough. Then in L infinity, not only do you remain close to the kink, but you approach the kink. So then norm phi of b, I suppress x minus k in L infinity behaves like constant epsilon root t if t is greater than equal 1. Okay? The theorem says much more because you can describe the asymptotic form of this wave, albeit not terribly well, and you will see a logarithmic phase correction, which I mentioned at the very beginning of this talk. You cannot hope to say that phi of t is well approximated by the linear evolution, the linearized evolution. No, because the linearized Sine-Gordon will have here a term which is localized. If I'm not mistaken, for Sine-Gordon, the first term here is stretch x, tanh x. Not so important what it is, maybe with a minus sign. So the quadratic term comes with a Schwartz function coefficient, and this is actually a catastrophe at first sight. How did I start this discussion? By saying that the cubic is dangerous because you can write it as 1 over TU. U will decay like 1 over root T. I will explain in a second why. 1 over root T U squared 1 over T. That's long range. But this is horrible. This is 1 over root T. This is hopeless. This is not just fails by a logarithm, the Duhamel formula, if you do something naive, it grows like root T. Okay, how can you treat this perturbatively? Well, you can. That's when normal forms come in. And there is a miracle that happens, which is something that here at ISOM in December 21, Thomas Kappeler, whom we then tragically lost and totally unexpectedly a few months later, pointed out that the vanishing I'm about to mention, which is so crucial for that theorem to work, might be, or we now believe he was absolutely correct, but it's not systematically studied in infinite dimensions, an expression of the integrability. We do not use the inverse scattering transform. Nevertheless, the vanishing that I should mention very soon, there's a magic non-resonance condition, which means what? The absence of a small divisor. For this is a expression most likely of complete integrability of the problem. Not only is this non-vanishing condition, and I should tell you what it is, absent 454. It is exactly the same as the Fermi golden rule. Would you have this vanishing quadratic non-resonance, the Fermi golden rule would fail. So your only hope to have this, what's it called? There is a name for this dispersion by coupling. So you have to couple the discrete spectrum to the continuous spectrum through the nonlinearity. I'm blanking. There is a catchy phrase for that. Do you remember? In order for this to kick in for 5-4, you precisely must not have what I'm about to write down. And before I do that, I should say that before us, there was a very important paper, at least to us, Chen Liu. Chen is now at Georgia Tech. I'm proud to say he was my former student at Chicago. This appeared in 20, I believe, 20 or 21. 20. And what they did is they did something much more general without an epsilon. Now you will say, well, you're kidding me then, right? But they used the inverse scattering principle. They used Riemann-Hilbert, D-bar, all the magic of completely integral equations. And they showed for generic data, please look at their paper, what that means. It's a very precise meaning in this complex analysis machinery that they use. For generic data, they're able to show not just asymptotic stability, but Soliton resolution. Yes, please.
So, what happens to the wobbling king?
The wobbling king, brilliant question. The wobbling king is excluded in their genericity. It's non-generic. Say it again. The wobbling king is excluded by this X. There, so, and in fact, Chen Liu Lu, so Benoit put his finger on an extremely important point. Chen Liu Lu were the first to understand that the optimal weight you can put there is root X. Otherwise, you will have problems with the wobbling king. Okay? Fantastic question. How badly am I doing with time? Catastrophically. 10 minutes, 5 minutes. Okay? So I want to say a few things, like what is the quadratic resonance? Then what did we do just recently, a few weeks ago? What did we publish for nonlinear Klein-Gordon? Where this magic vanishing does not happen. So what's the magic non-resonance condition? This can go, the spectra we know. They have solved their purpose. So what's the biggest open problem in the field? To prove something like this for all data for 5-4. Not known. Seems to be very, very difficult. Okay?
And to remove the messy in
That's what we're working on now. That's much easier than 5-4. The internal mode for 5-4, you have, you see, that's why Jonas and I started working on nonlinear cubic Klein-Gordon, because it has some features of 5-4, but not the internal mode. But it has a quadratic resonance.
For you, it's easier that it's going.
Say it again.
For you, it's easier that it's going instead of being inside in the gap.
Yeah, that is easy to remove by, say, Lyapunov-Perron construction of center stable manifolds. Easy is not the right thing to say, but there is in fact, a paper by Kowalczyk, Martel, Munoz, I forget the exact authors. What did they do? They took nonlinearity slightly above cubic. Okay? Then you have an easier time. You don't have a threshold resonance, but these are words that I haven't even defined to my dismay. Because what I should have brought up is, first of all, these potentials, these Schrödinger operators on the line, they're very, very special. They're all of the Pestel-Taylor kind.
I guess so. Is the intuition that for Klein-Gordon Sweden, the bad mode is so unstable that it goes.
Yeah, you project it on the linear level. On the linear level, you have a center stable manifold. You have to construct this thing. On the linear level, you have a tangent space. And the tangent space is that you're perpendicular to these. Remember this picture I drew of the spectrum? Here you have these two bad guys. So what you have to do is you have to project away from this guy pictorially, okay? Because you now have a system, 2x2 system. Project away from that gives you your tangent space. And then you have a non-linear correction near here. Everything's near, yeah? So what is this point? This point is the Q, the solid one. So that's fairly standard to remove the exponential stability. So our theorem with Jonas, of course, is conditionally on some form of center stable manifold. Okay, but well, let me get there if I can. But this is a fascinating story. All of these potentials are actually part of a Pestel-Taylor hierarchy, which is HL is minus dx squared minus LL plus 1 sec squared x. Okay? And there is a miracle going on here, which is also very important for us. You can do what's called the Darboux transformation. So that I don't mess this up, they're operated Bj, which are
it's minus dx squared plus
and minus del x squared minus LL plus 1 sec squared x. And L is an integer. Starting with 0, if you take 0, you get just minus del x squared. You're wondering about this. This is the second of the hierarchy. This is the first of the hierarchy. And this is the second of the hierarchy after you change variables. Okay? You get the 6 back. And so what's this Darboux transformation? You might think that this is some kind of completely integral magic, but it isn't really, because what you can say is D1 DL. So you take an operator, the differential operator for the L, you hit HL with it from the left, and then what it does, it spits out the free guy, which is H0, with these operators on the right. Isn't that amazing? Check it. Try proving it. What could be easier? You have an explicit L here is 0, 1, 2. 0, of course, is silly, so that's not part of Pestel-Taylor, but 1, 2, and so on. And then you have this magic vanishing act. The potential is removed. And that's very important for us. Why? Because here we did not use the distorted Fourier transform. We magically removed by Darboux transformation. So you take B1, you apply it to your linearized, which is written there, linearized equation, nonlinear equation. The left-hand side becomes nice because now you have the flat case, you have no potential. But on the right-hand side, you have differentiated, and then U is still there. So what you have to do, you have to invert this. So you have an integral operator. but you can still pull it off. Listen, I must be torturing you. So why don't I talk about the quadratic, what that means, quadratic resonance? Then I should talk about the new theorem, so 10 minutes, then I'm done. Okay?
Only the new theorem is for next time.
Very good. If there is a next time, yes. If meaning, no, let me specify. If you still want to hear about this next time, there will be a next time, but maybe you don't want to hear about it.
Now it will relax to come back.
Now you are so hungry for this that you want to come back to. Are you sure? So what's the quadratic non-resonant condition? You can see it with or without double transform. Let me do it without double transform, since you guys are dealing with the distorted Fourier transform. What is the distorted Fourier transform say for, in this context, you would be dealing with this. So what is the distorted Fourier transform? You have H F plus minus is C squared F plus minus. We are now on the line, not like for Coulomb on the half line, and you have to worry about what happens at 0. Here you have to worry about what happens at minus infinity plus infinity. And this is a beautiful, it has a nice Schwartz potential. And what is the, so these are eigenfunctions, only size real, so they are, remember in October, Van-Titchener solutions, but the limits of Van-Titchener solution as the complex energy approaches the real axis. So these are asymptotic to e to the plus minus I x psi, as x tends to plus minus infinity, all right? So they're asymptotically free waves. And then it so happens, well, first of all, I should tell you what transmission and reflection coefficients are. So here is your potential. When you send in a wave, here, part of it gets reflected, part of it gets transmitted, okay? How do you formulate this in terms of these so-called Yost solutions? You say that you send in e to the I x psi, but we have to correct this a bit. Asymptotically at minus infinity, you send it in this. Incoming, you get an outgoing wave, and you have a outgoing to the right, which is the transmission coefficient. Here I forgot the reflection coefficient. Transmission coefficient times that. Only you can't do this, you have to put F plus. You can't do this, you have to take F minus dot minus psi. Look at the formulas. And this, no, you have to take F minus dot psi. What is this mysterious picture? It's just an equation, and the equation is that this solution, which after all is global, you can ask me, does such a thing exist? Yes, by Volterra equations, it exists, and that has to equal the sum of these two pieces. So you get F minus x minus psi plus R of psi, F minus x psi. Did I do this right? So this equation is the meaning of this picture. It's just one piece getting here. Okay? Why did I write this down? Because the distorted Fourier transform, which again Jonas and I did not use there for a particular reason, because these operators all have so-called threshold resonances, and then what I'm about to tell you is discontinuous at 0. And only recently Gonchen and Pusateri found the trick exploiting some special symmetries to get around that. So in principle, one could also use this here. So what's the distorted Fourier transform? It is to define Ex psi, looks a little bit strange, 1 over 2 pi, T of psi, F plus X psi, and then you have T of minus psi, F minus X minus psi. Notice in the free problem, the transmission coefficient is 1, the reflection coefficient is 0. What you send in comes out. So then you have e to the ix psi, e to the minus ix minus psi. So all of this is just e to the ix psi. This is for psi positive, this is for psi negative. Okay? And then you have an issue that where you break, you might have a jump. And you have a jump if and only if you have a so-called threshold resonance at psi equals 0. Here, I should really, no, this is minus m squared. So m squared are these numbers. Okay, the mass terms. You have to move the threshold to 0 for this to make sense, okay? So this guy is minus dx squared plus v, and v looks like that. Okay? Let me not get technical. What you really need is x times v in L1. Then these your solutions are continuous as you send psi to 0. Okay? What is the distorted Fourier transform? It's the following identity: ex psi tensor ey psi bar the psi integrated from minus infinity to infinity equals what? Delta 0 up to a constant x minus y. That's the distorted Fourier transform. As I said, it may happen to you that you jump because of a problem at psi equals 0. What Chen and Pusateri realized is that suppose you multiply this by -1 and this by -1, you change nothing because -1 squared is 1. Okay, so this silly remark of mine helps because if you are exactly symmetric, if you jump it from -2 to 2, then you multiply by -1, then you become continuous. Does it make sense? Their trick only works then. Now, we know what the distorted Fourier transform is. What is the quadratic non-resonance condition that intervenes here? I have to tell you what the threshold resonance is. For HSG, H sine Gordon, there exists a solution at the threshold. The threshold of the continuous spectrum is 1. So there exists an L infinity solution, phi in L infinity, but not L2. Okay? This is not an eigenfunction, cannot be. You cannot have at the threshold eigenfunction if your potential behaves like this. I can explain why in a minute. So you can only have a bounded solution. And what did we say for Sengoria? The 0 mode that has no crossing, so that's positive, the ground state at 1. So here you must have by Sturm oscillation 1 crossing. I think the phi is totally explicit and it's set hedge. No. It is hedge. Hedge. Okay? And this is called a threshold resonance. You know that I'm picky about using resonance. It always means what? A small divisor. Where's the small divisor? You see it, like Ibra explained, if you Laurent expand the resolvent around the threshold energy. You look at the Laurent expansion of what? H minus, I have to move the threshold to 1, so H minus 1 minus Z squared to the -1 will now start with basically phi tensor phi. Notice this is not an L2 operator over Z plus big O1. And here in Z is positive and Z tends to 0. Okay? This is a projection, formally speaking. You know what phi tensor 1, phi tensor phi is. It's the conjugate phi of x times phi of y. Okay? And notice that it doesn't start with the 1 over Z squared, the Laurent expansion in what Hilbert space in a weighted L2 space. Okay? It starts, if it were to start with 1 over Z squared, this would have to be an eigenvalue. Eigenfunction cannot be at the threshold. It starts mysteriously with a Z. That is the small divisor. And I wanted to explain to you what this actually does to the time evolution. You see, I haven't even written down a linear estimate that explains why the free decay is 1 over T. Disaster. That I haven't done that. So maybe next time. If you still have the patience to listen to me rambling. Okay? No. So finally, what is the quadratic non-resonant condition? It's this. You take the distorted Fourier transform script f that uses the basis e. You take your coefficient alpha, which is sec10, you multiply by phi squared, and then at plus minus √3, you get 0. That is the magic quadratic non-resonant condition. What does it do? It allows you to apply normal forms in the quadratic term. And for nonlinear Klein-Gordon, this fails. For phi4, it fails. Where does this funny number come from? It comes from the quadratic term in Duhamel because what? Because you will see that you have an integral like this, 1 to t, then the time evolution will give you a term e to the is, Japanese bracket psi, which is what? That's the symbol of the free problem, 1 plus pi squared. Then you have your coefficient, you have to multiply by phi squared, you take your, this means distorted, Fourier transform at psi. Then because of this 1 over √t decay here, this is the Duhamel integral, so you get an s. And then you still have an oscillation coming from the threshold of the spectrum, that is 2in. This is your enemy once you apply the distorted Fourier transform in s. Now notice something. Where does the combined phase, this is plus minus of course, where does the combined phase vanish? It vanishes when 2 minus Japanese psi is 0. That means 4 is 1 plus psi squared, so psi is plus minus √3. This is exactly where you have a so-called time resonance, where the phase vanishes. Now notice, if this vanishes at √3, then you can integrate by parts in S, and you don't have a small divisor, because numerator, denominator, is simple 0. Okay? And that is the reason for us that we can go to infinite time here. Okay, thank you. Sorry.
Oh,